Hello students, welcome to EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk about Lie algebra. In this module, we will discuss the representations, the Clebsch-Gordon coefficients, and examples from isospin using Lie algebras. All this is from the paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, hopefully you will learn techniques to study Lie groups through the algebraic approach. You will learn to construct single particle states of arbitrary angular momentum and then learn to use these techniques in physical problems, for example, in problems involving isospin. It is generally more efficient to take the algebraic approach in the study of Lie groups. Lie algebra is the study of the structure of the group in terms of commutation relations of the generators. For the Lie groups SO3 and SU2, for example, we already saw that the number of generators equals to the dimension of the Lie group, which is 3 for both these groups SO3 and SU2. We saw that the generators of these groups being 3 designated as J1, J2, J3, they satisfy the commutation relation that the commutator Jij J is equal to I epsilon Ijk Jk. This is true for any general Lie group GL. We can find its finite dimensional set of generators. Let the group has n generators, T is equal to T1, T2, Tn, etc., which will close under some commutation relations. The commutator Ti Tj is equal to Cij k of Tk. So they form a closure, and Cij k's are n by n matrices. They are labeled by k, and these are called the structure constants of the Lie algebra. So we have Ti's, which are the generators of the algebra. They satisfy a commutation relation under which they are closed, and the Cijk's are the n by n matrices, which are called the structure constants of the Lie algebra. The structure constants are invariant under a change of representation. We will first prove that the structure constants are invariant under a change of representation. That is, the structure constants Cijk is invariant when the generator Ti is transformed to Ti prime by a unitary transformation U inverse Tiu. To see this, let us consider the commutator between these transformed generators, namely commutator Ti prime, Tj prime is equal to the commutator U inverse Tiu, U inverse Tju, which is equal to U prime multiplied by the commutator between Ti Tj into U, but the commutator Ti Tj is equal to Cijk Tk. So therefore this can be written as U inverse 1 Cijk Tk U. Now we introduce U inverse between Cijk and Tk to write this as C inverse Cijk U inverse Tku, and U inverse Tku is then Tk prime. Therefore this is equal to U inverse Cijk U Tk prime, which is equal, but Ti prime Tj prime, this is the commutator of the generators, which is equal to the Cijk Tk prime, which implies that Cijk is equal to U inverse Cijk U, which means the structure constants are invariant under a change of representation. The commutation relations between the generators Ti Tj, They satisfy an important identity called the Jacobi identity, which means if you have generators say A, B, C, then the commutator of AB with C plus the commutator of BC with A plus the commutator of CA with B is equal to 0. This is an important identity which is satisfied by the generators of the Lie group. Further, the Lie algebras form a linear vector space under vector addition and scalar multiplication. That is, if there are two vectors x and y belonging to a linear vector space GL, and if you have two numbers VLO complex A and B belonging to a set of VLO complex numbers, then if x and y belong to the linear vector space G, then a linear combination AX plus BY also belongs to the group G. And moreover, the commutator XY also belongs to the GL, which means that the closure property is satisfied, and this relation XY belonging to GL follows from the commutation relations. The maximum number of mutually commuting generators of a Lie group is called its rank. An operator which commutes with all the generators of a Lie group is called a Casimir operator for the Lie group. Number of Casimir operators is equal to the rank. This is given by the Raka theorem, which we are not going to prove here. So we are interested in finding all the representations of the Lie group. Obviously, the set of matrices defined by the structure constant Cij of K of the Lie algebra themselves form a representation. This representation is called the adjoint representation. The other representation satisfying the same algebra as the generators can be obtained by exponentiating, that is, any representation D of T can be obtained from the generators T1, T2, T3, etc. by exponentiation, that is, D of T is equal to exponential of I sigma alpha I Ti, where I is sum over all generators. We do not know anything about the matrices Ti, nor about their dimensions. We, however, know the fundamental representation. What is the fundamental representation? Fundamental representation is the representation of generators of the Lie group. This will generate one representation through the exponentiation. A systematic generation of all possible representations can be made by the ladder approximation method, which we will illustrate for the case of the Lie group SU2. So let us illustrate this for the case where J is equal to half. So when J is equal to half, how many states are there? Total number of states 2J plus 1, 2 into half plus 1 is equal to 2. So the number of states are, there are two states which we will call as spinor states corresponding to M is equal to plus minus half. So these two states can be written in terms of two-dimensional column vector, which is called a spinor. So we have a state corresponding to J is equal to half, M is equal to half, which we represent as half half, which is a two-dimensional column vector 1 0. And the second state correspond to J is equal to half and M is equal to minus half, and which is represented by the column vector 0 1. Let us, what does J3 do to the state 1 0? J3 projects the value of M. And what is the value of M for the state 1 0? Half. So J3 acting on 1 0 is half 1 0, and likewise J3 acting on 0 1 is minus half 0 1, and J plus acting on 1 0, what would it be? It would be 0, because M is already plus half, which is the maximum value. So J plus cannot further increase. So J plus acting on 1 0 is 0. Likewise, J minus acting on 0 1 is equal to 1. Whereas J plus acting on 0 1 increases the value of M by 1. So from minus half to half. So J plus acting on 0 1 is 1 0, and J minus acting on 1 0 is 0 1. So we can now, from these relations, that is from the action of J plus J minus J3 onto the two states 1, 0 and 0, 1, having obtained that, we can write down then a representation for the operators J1, J2 and J3. So for example, if you write J1 as a 2 by 2 matrix, J1 is equal to half with 0, 1 and 1, 0 in the first and second columns, and likewise for J2 and J3. So this will form a representation. Now notice that J1, J2, J3 are nothing but again the Pauli matrices. So the representation of SU2 for J is equal to half are obtained. So what we have seen, so J's are nothing but the Pauli matrices, and all the other representation of SU2 for J is equal to half is then obtained by the general rule of exponentiating these matrices. That is, any other representation for J is equal to half, that is D half theta I, is obtained by exponentiating is equal to exponential I theta I Ji, which correspond to the spin angular momentum half. So we have seen that the Pauli matrices form a fundamental representation of SU2 group, and other representations can be obtained by exponentiating it. So let us now see what happens when J is equal to 1. So when J is equal to 1, how many states are there? 2J plus 1, which is equal to 3. What are the possible values of M? Goes from minus J to J plus, so that means plus 1 to minus 1 is in the steps of 1. So possible values of M are 1, 0, minus 1. And we can then write a 3-dimensional representation. Earlier, for taking J is equal to half, we obtained a 2-dimensional representation. We now obtain a 3-dimensional representation. Now consider the eigenstates 1, 1, 1, 0 and 1 minus 1. That means 1, 1 means J is equal to 1, M is equal to 1. 1 minus 1 means J is equal to 1, M is equal to minus 1, and so on. We can write these as column vector in 3 dimensions. 1, 1, 1 can be written as a 1, 0, 0, a column vector with the first row 1, second row 0, third row, and likewise 1, 0 is 0, 1, 0, and 1 minus 1 is 0, 0, 0, 1. Now using J3 acting on 1 plus minus 1 is equal to plus minus 1, etc., and J3 1, 0, 1, 0, and J plus minus acting on 1, 1 is J minus acting on 1 minus 1 is equal to 0, because J plus acting on 1, 1 means the maximum value of state 1, 1 is M is equal to 1, and J plus cannot raise it further. Therefore, J plus acting on 1, 1 is 0. Likewise, J1 acting on the state 1 minus 1 is 0, because 1 minus 1 is a state with the minimum value of M, which is minus 1, and J plus will increase the acting on the state 0 will increase it by 1, and so on. So we have then these relations that J plus acting on 1 plus minus 1 is equal to root 2, 1, 0, and J plus acting on 1, 0 is root 2, 1 plus minus 1. So from these operations of J3, J plus, J minus onto the 3 states which we have defined as 1, 1, 1, 0, 1 minus 1, we can write down J plus, J minus and J3 as a 3 by 3 matrix. Or alternatively, which means we can write J1, J2, J3 as 3 by 3 matrices, which are shown here. Namely, for example, J3 is a diagonal matrix with the diagonal elements 1, 0, minus 1. And J plus is a 3 by 3 matrix. So the first column is 0, the first root 2 in the second column, and in the third column it is 0, and so on. So this is a 3-dimensional representation. We will now discuss the product representation. So let's consider 2 eigenstates labeled by J1M1 and J2M2. These are the eigenstates of the operators J1 square, J1G, and J2 square, J2G respectively. Now we define the product eigenstate as denoted by J1M1 with the direct product with J2M2, which we write as J1M1, J2M2. This is the product of individual eigenstate. that is the product eigenstate is denoted by as the product of individual eigenstates. And how many states are there? There are 2J1 plus 1 eigenstate J1M1. There are 2J2 plus 1 eigenstates J2M2. Therefore, the total number of product eigenstates is 2J1 plus 1 multiplied by 2J2 plus 1. So, these product states which we have represented as J1, M1, J2, M2, they satisfy the property that, for example, J1 square acting on this product state J1, M1, J2, M2 actually only on the part J1, M1, and J1 square acting on J1, M1 is J1 into J1 plus M. Therefore, J1 square acting on this product state J1, M1, J2, M2 is equal to J1 into J1 plus 1 and the state J1, M1, J2, M2. Likewise, J1 Z component of this acting on the product where J1, M1, J2, M2 is simply equal to M1 into the product state J1, M1, J2, M2. These 2J1 plus 1 into 2J2 plus 2 states, they transform according to the product representation dJ1 into dJ2 of SU2. This representation can be reduced to a sum of irreducible representations because this direct product representation need not be, in general, is not irreducible, but it can be reduced to a sum of irreducible representations where each irreducible representation dJ occurs once for all values of j. What are the possible values of j in the product representation or in the product state? The all possible values of j lie between j1 minus j2 magnitude and j1 plus j2 in steps of 1. So, each representation has 2j plus 1 states which are linear combination of j1 m1 and j2 m2. So, the number of these states in the product is then equal to 2j plus 1 sum over all values of j from j1 minus j2 modulus to j1 plus j2, which is equal to 2j1 plus 1 into 2j2 plus 1. For example, consider two states of angular momentum 1. So, for these two states of angular momentum 1, which we want to now get a product of these. So, how many states? Let us see. We have states of angular momentum 1. That means j1 is equal to 1, j2 is equal to 1. So, what is the total number of states? Total number of states is 2j1 plus 1 multiplied by 2j2 plus 1, which is equal to 9. When you have combined state where each state is of angular momentum 1, then the total number of states is equal to 9 in all. And the combined states transform according to the value of, what are the possible values of sum of the j1 and j2? 2, 1 and 0. So, the combined state, there are 9 of the states which transform according to the values of j is equal to 2, 1 and 0. Number of states corresponding to the j value 2 is 5, 2j plus 1, 1 is 3, so 5 plus 3, 8 and 0 is 1. So, there are 9 states, 5 of those states transform with angular momentum value 2 and 3 states with angular momentum 1 and 1 state with angular momentum 0. And these are the states then obtained by vector addition of j1 and j2. So, thus the corresponding number of states are given by sigma 2j plus 1, where j takes all the possible values from j1 plus j2 to j1 minus j2 in steps of 1. So, j goes over 0, 1, 2, etc. So, in this case, we have the 9 states. So, in general, the combined state can be expressed in terms of j and m, capital J and capital M, obtained by taking the sum of all product states j1, m1, j2, m2 with the corresponding weight C, j1, m1, j2, m2 and jm is resultant state by summing over all m1 and m2, m1 for example going from j1 to j2, m2 and likewise m2. Now, these coefficients can be obtained by using the orthonormality of the state j1, m1 and j2, m2. So, we obtain the state coefficient C, j1, which is incidentally called the Clebsch-Gordon or the Wigner coefficient. This can be obtained, for example, by using the normal orthonormality of the states J1, M1, J2, M2. So C J1, M1, J2, M2, semicolon Jm, this is the Clebsch-Gordon coefficient, is obtained by taking this product, scalar product of the states capital Jm with the product space J1, M1, J2, M2. And then the product space can be specified by quantum numbers capital J and capital M. So in terms of the product spaces, it can be written as a capital J, capital M state. The product space specified by these can be written as a linear combination of the product spaces with the weights which are given nothing but the Clebsch-Gordan coefficients. So we will now show that the Clebsch-Gordan coefficient or this scalar product capital J, capital M with the product states J1, M1, J2, M2 is equal to 0 unless capital M is equal to M1 plus M2. Let us operate on the state by Z component Jz which is equal to J1G plus J2G. So our state is Jm. So when we operate with Jz, then Jz operating on this state Jm will project, that means capital M Jm is equal to J1G will operate on the state J1 and J2 will operate on the state J2. So therefore M multiplied by this state Jm is equal to M1 plus M2 and then the product states J1, M1, J2, M2 and the corresponding Clebsch-Gordan coefficient, sum over all values M1 and M2, which gives us the following relation. The capital M minus sigma M1 plus M2 multiplied by the Clebsch-Gordan coefficient and the state J1, M1, J2, M2 is equal to 0. Since J1, M1, J2, M2 are independent for different values of M1 and M2, this means that M minus M1 minus M2 acting on this J1, M1, J2, M2, Jm is equal to 0, which implies that J1, M1, J2, M2 acting on Jm is equal to 0 unless M is equal to M1 plus M2. What does it show? It shows that the Z component of the total angular momentum is equal to the sum of the Z components of individual angular momentum. This is an interesting, important result. To emphasize, the Z component of the total angular momentum means the angular momentum obtained by adding vectorially the angular momentum of the two individual states J1 and J2. So what we have shown is that the Z component of the total angular momentum must be equal to the sum of the Z component of individual angular momenta. I will now discuss another application of this from the field of isospin, which is akin to the ordinary spin, but it's called isospin because this is in a different space, which is called the internal space. How does the concept come? We know that the strongly interacting particles form multiplets under isospin. For example, the nucleons, the pions, the deltas are represented in the following manner. See, we have two nucleons, proton and neutron. As far as the strong interaction is concerned, the proton and neutrons behave almost identical and they differ only in their electromagnetic interactions. So the nucleons, if you work of strong interactions alone, can be represented by a doublet whose two components are proton and neutron, and likewise the three pions of charges plus, minus and 0 can be clubbed in a triplet with respect to the strong interactions, and the delta particles are the particles with doubly charge, singly charge and so on. So delta particles, there are 4 in number. There is one doubly charge, one singly charged positive, one singly charged negative and one neutral particle. So when these particles written or represented as a doublet for the nucleons, a triplet for the pions, and in the 4-dimensional column vector for delta, this just like the spin half for the proton neutron, and spin 1 representation, which you have the J is equal to 1 representation for the pions, and for example J is equal to 3 by representation for the deltas. So instead of being the representation in the rotational space, we call it isospin. So the nucleons, pions and deltas can be represented by an isospin half, 1 and 3 half respectively. The charge of a particle in this multiplet is given by what is called a Gell-Mann-Nishijina formula, which is that the charge of a particle is I3 plus Y by 2, where I3 is the value of the third component, like J3 is like M, and Y is the hypercharge, which is equal to 1. Isospin is equal to half an integer multiplets, and Y is equal to 0 for integer multiple pions. So, having designated these particles or written this particle in the form of a doublet, triplet, so on. Now let us see how what we have learned help us in understanding some of the properties of these particles. Now it was found the particle delta plus decays into two different modes, and of course the decay must certainly conserve charge. So it was found that delta plus decays into a neutron and a pi plus, and it also decays into a proton and a pi 0. And what was found was that the decay of delta plus into a proton and pi plus is twice as fast as the decay of delta plus into a neutron and a pi plus. Now, this kind of observation that the decay of delta plus into a proton and pi plus is twice as fast as the decay of delta plus and pi plus, and the other observations, they can be easily understood or explained from the group theory point of view by assuming that the strong interactions laws are invariant under the isospin transformation. So, if isospin is a good symmetry, then in the presence of isospin symmetry, the particle states are simultaneously eigenstate of I square and I3. Just as if rotational symmetry is a good symmetry, the state can be represented eigenstates simultaneously of J square and Jz. So, in the same manner, similarly, if isospin is a good symmetry, then the particle states are simultaneous eigenstates of I square and I3 operators. For example, if proton is defined by spin half as a state with half-half, where means the I spin is half and the Z component of that is half. So P, just like the state earlier in the angular momentum case, was designated as half-half. So the proton state is designated as half-half. The corresponding neutron state will be half minus half. Pi plus is 1, 1. Pi 0 will be 1, 0. Pi minus will be 1, minus 1. Delta plus plus is 3 half, 1 half, and so on. As we have seen earlier, the product eigenstate, because we are considering the decay of delta into a pion and a nucleon. So we consider the product eigenstate of a pion and nucleon. And these product eigenstates are the product of individual eigenstates, and they transform according to the product representation, which we have seen, and which can then be reduced to a sum of irreducible representations. From the nucleon and pion state, how many states can be formed? There are 2 nucleon states and 3 pion states. So there are 6 different nucleon states. And the eigenstate of I square operators have the total value of 3 half and 1 half. Thus, we have to decompose 2 into 3 into the states 4 plus 2, where 2, 3 and 4 correspond to 2, 3 and 4 dimensional representation associated with the spin half, 1 and 3 half respectively. Delta plus state is given by a 3 half state. So delta plus can be written as 3 half, and therefore I minus acting on delta plus will be, now from what we have learned earlier, root 3, 3 by 2 half, and 3 by 2 half is delta plus. So it's just root 3 times delta plus. And likewise, I minus acting on product state proton pi plus is I minus acting on proton, then I minus acting on pion. So minus acting on the product state proton and pi minus gives us a product state between neutron and a pi plus, and root 2 times the product state between proton and pi plus. Thus, delta plus is 1 by root 3 I minus delta plus, which is 1 by root 3 n times the product state n pi plus root 2 times p pi plus, and therefore the decay rate of delta plus n pi plus and its ratio of delta plus to pi plus is 1:√2 because n pi plus and p pi minus occur with a relative weight of √2 with p pi minus. So p pi minus occurs √2 times more than the state n pi plus. Therefore, the decay rate, which is the square of this, the decay rate of delta plus p pi plus is twice as much as the decay of delta plus into n pi plus. To give an example, for a given value of j could be 0, half, 1 or 3/2. So we start from any state which is specified by the eigenvalues j and m. Then by repeated application of the raising and lowering operators which we had defined earlier, that is, by repeated applications of j plus and j minus, we can construct all the states with the eigenvalue m lying between minus j to j in the steps of 1. So there are a total of 2j plus 1 state. So starting from one state, we can construct all the 2j plus 1 states. In other words, for a given j, we can construct 2j plus 1 states of different m. Thus, the dimensionality of the vector space of the eigenvector jm is 2j plus 1, which has to be an integer. Therefore, j can take either an integer value or half an odd integer value. We will now illustrate the method for constructing representation in the following way. Consider a state corresponding to j is equal to 0. There is one state only, it's a singlet state. Therefore, when it is operated on by the lowering or the raising operator j plus minus, it gives 0. So j plus minus, j square and j3 acting on the singlet state corresponding to j is equal to 0, m is equal to 0 is equal to 0. So in this case, for j is equal to 0, there is only one representation which is one dimensional. Now I will discuss representations of SU2 algebra by a method known as the ladder operator method. Consider a set of matrices D1, D2, D3 which satisfy the same algebra as the generators of the Lie group. Namely, the generators of the Lie group satisfy the algebra Jij commutator is equal to epsilon ijk, where in this case epsilon ijk are the structure constants. Then the representation D1, D2, D3, etc. satisfy the same commutation relations, meaning the commutator di dg is equal to I epsilon ijk dk. Now, if this is satisfied, then the d's are called a representation. For example, if we write di is equal to sigma I by 2, where the sigmas are the usual Pauli matrices, then sigma I by 2 forms a fundamental representation. This is called the fundamental representation. In order to obtain other representations from the fundamental representation, we define what are called the raising and lowering operators, with which you may be familiar from your quantum mechanics. So we define an operator j plus minus, where j plus is called the raising operator and j minus as the lowering operator, by the definition that j plus minus is equal to j1 plus minus ij2. Obviously then j plus minus dagger is equal to j minus plus, and the commutator between j plus minus and j3 can be easily obtained from the commutation relations satisfied by the generators of the Lie algebra. So we have the commutator j plus minus j3 is equal to minus plus j3, and the commutator j plus and j minus is equal to 2j3. So having obtained this commutation relations, now let us consider an eigenstate of j3. Let we represent by a vector m as an eigenstate of j3 with the eigenvalue m, that is J3 acting on m is equal to m on m. Now J3 Jm acting on m from the commutation relation between J3 and Jm can be written as J plus J3 plus Jm acting on m, but J3 acting on m projects value m, so this is equal to m plus 1 J plus acting on m, and likewise J3 J minus acting on m is equal to m minus 1 with J minus acting on m. So what does it mean? It means that J plus and J minus are the raising and lowering operators which increase the eigenvalue of J3 by 1 unit, because you can see that J3, the eigenvalue of J3 acting on the vector J plus m is equal to m plus 1 J plus m. So J plus m is an eigenvector with an eigenvalue m plus 1. And likewise, J minus acting on m is an eigenvector with J3 with eigenvalue of J3 equal to m minus 1. Thus, J plus and J minus, they increase or lower the eigenvalue of J3 by 1 unit. We can also define the total angular momentum J square as the sum of squares of the three components, that is J square, so J1 square plus J2 square plus J3 square, which can also be written in terms of raising and lowering operators as 1/2 of J plus J minus J plus J3 square. And since J square, the sum of the squares, is always greater than or equal to 0. And the definition of J square, we can see that J square commutes with all the components of J. That is J square commutator with Ji is equal to 0 for all i's 1, 2, 3. So J square commutes with all Ji's, but it doesn't mean that Ji's commute among themselves. The rank of this Lie group SU2 is 1, because there is only one operator J square which commutes with all the generators. We can therefore take J square and J3 be a set of commutating operators, and since they are set of commutator operators, they share a common basis for eigenfunctions. We choose the state to be the eigenstate of J square and J3 with the eigenvalues lambda and m. So we represent an eigenstate, which is the eigenstate of J square and J3, by specifying two numbers lambda and m, such that J square operating on this eigenstate lambda m projects the eigenvalue cos of J square, which is lambda. So J square acting on lambda m is lambda times the eigenstate lambda m, and J3 acting on lambda m projects the value m. And further, we normalize these states by saying that the scalar product of these two states, lambda m, lambda prime, m prime, is equal to 1, provided lambda is equal to lambda prime and m is equal to m prime, otherwise 0. J square is greater than 0 because J square is positive, which implies that m square is always less than or equal to lambda. Since J square commutes with all the generators of the group, then from Schu's lemma, it can be represented by a multiple of identity matrix in any irreducible representation. So, J square can be represented by an identity matrix. Since J plus minus acting on the state lambda m are eigenstates of J3 with eigenvalue m plus minus 1, which means we can write J plus minus acting on lambda m is equal to some number C, which will represent as C plus minus function of lambda m acting on the state lambda with m plus minus 1. Because J plus minus increases the value of m, increases by a unit number, and J minus lowers it. So J plus minus acting on m gives us a state with m plus minus 1. C plus minus lambda m are constants which have to be determined from the normalization, and since J minus m square is always greater than or equal to 0, eigenvalues m square are bounded. Let the largest value of m be J. We then have J plus acting on lambda J is equal to 0 because the largest value of m is J. So it can't be further raised. So J plus acting on lambda J is equal to 0, and J square which is equal to half j plus j minus j plus j square, etc., gives me the j square acting on lambda and j is equal to j minus j plus j3 square plus j acting on lambda j, which is then can be seen to be equal to j into j plus 1 lambda j. So the eigenvalues of j square acting on the eigenstate lambda j are j plus 1. So likewise, let us assume that the smallest value of m be j prime, which means that the operator j prime acting on this state with the smallest value of m, which we have designated by j prime, that is lambda minus acting on lambda j prime is equal to 0, because it's already operating on the eigenvector or eigenstate with the lowest value of j prime. It cannot be further lowered, which implies that lambda is equal to j prime into j prime minus 1. Thus, we have j into j plus 1 is equal to j prime into j prime minus 1. That means that either j prime is equal to j plus 1 or j prime is equal to minus j. But j prime is equal to j plus is not allowed, because j is the largest value already. Since j minus decreases the value of m by 1 unit each time it acts on an eigenstate of j3, this means that the maximum and minimum values of m differ by an integer. That is, j minus j prime is equal to 2j, which is an integer, which implies that j can only take up values which are integer or half an integer. So j is either an integer or half an odd integer. That is, the possible values of j are 0, half, 1, 3 half, etc. We can use then j to label the states instead of lambda. Therefore, label our state as lambda m such that j square acting on this state jm is equal to j into j plus 1 and the state jm, and j3 acting on jm is equal to m times jm. So what does it mean? It means the state Gm is an eigenstate of two operators j square and j3, because j square is the only operator which commutes all the other generators. So in general, the state can be designated by just giving two numbers j and m, such that j square acting on the state jm projects out the value j plus 1, and j3 acting on this state jm projects value m. So what happens to j plus acting on jm? So the way we have defined j plus acting on the state jm is equal to c plus jm, and j plus, what does j plus does? J plus increases the value of m by 1 unit. So it takes the state jm to the state jm plus 1. And likewise, j minus acting on jm takes the state to a value of m which is 1 unit lower. So j minus acting on jm is c minus jm acting on jm minus 1. Therefore, we can see that this constant c plus jm whole square can be written as the expectation value of j minus j plus between the states j and m. Therefore, c plus jm whole square is the expectation value of j minus jm between the state jm, and j minus j plus can be written as j square minus j3 square minus j3, and therefore what you get is that this is equal to j minus m to j plus m plus 1. Therefore, c plus jm, which is called the Clebsch-Gordon coefficient, it can be written as the under root of j minus m into j plus m plus 1, and likewise c minus jm is j plus m into j minus m plus 1. So we can summarize what we have seen so far. What we have seen is that the state jm, where m takes now 2j plus 1 values, and the minimum value of m is minus j, and the maximum value of m is plus j, and all the other values which are obtained by in unit steps from minus j to j, which are 2j in numbers. So the states jm, they are 2j in numbers, they form the basis of the irreducible representation characterized by j. So students, let us summarize what we have learned in this module. The set of matrices defined by the structure constant Cijk of the Lie algebra form a representation itself. This is called the adjoint representation. The fundamental representation, on the other hand, is the representation of the generators of the Lie group and the states Jm corresponding to M from minus J to J in steps of 1 form a basis of the irreducible representation of SU2. Thank you.